Warning, do not attempt anything you see in this film without direct parental supervision or parental guidance. And always remember, safety first, protect your noggin, and always wear eyeglasses.
Hello? 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 Hey, I knocked. You guys got a phone? Whoa. Wait a minute.
Come on, gang! It's time to go!
Oh, that can't be good.
All personnel, it is now 1 minute to zero time. Put on goggles or turn away. Do not remove goggles or face first until 10 seconds after your first light.
Oh, that can't be good at all.
Hold up! Она зайдется! Wait! 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 Stop! Sure, great! Don't wait for me!
Minus 15 seconds. Minus 10 seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
Now that we've seen the movie clip of how this actually happens, I will explain the physics and the math behind what just unfolded in front of your eyes there. So the way I'm going to explain this is a series of physics equations. All these physics equations can be related to math, calculus, any type of math you want to be sorted for. So to do this, we're going to start off with force equals mass times acceleration. So your force equals your mass times your acceleration. Now, acceleration in calculus terms would be your a of t. So to start this off, we used a 200 megaton nuclear explosion. That's my assumption of what we used for that bomb that went off in Indiana Jones. So looking that up, we found that the force is 2,940,000,000 newtons. And that equals the mass of the bomb, which is 40,823.31 kilograms. And then that's multiplied by the acceleration. So the first thing we need to do is we need to find out how fast that refrigerator accelerated off of its base in the house. That's what we're trying to figure out first. So to do this, it's simple arithmetic. All you gotta do is divide it. You find out that your acceleration equals 72,017.68 meters per second squared. That's how fast the refrigerator accelerated off its base, flying in some odd direction. Next thing we need to do is we need to find out how fast, at the base of this explosion, how fast was this thing moving? What was the velocity? What was the v of t? Now, to do this, we need to use this acceleration right here, and what we know. So, first off, let's draw a quick diagram. So, drawing the diagram, we're just going to show what happened here. So, we're going to go off with a little angle here. So, we're going to know that this right here is 45 degrees. Because we're going to assume that it hit something when it came off. Like it hit like a chair or hit a couch or something in the house when it flew off. So what we need to do is we need to figure out the velocity and when this started. So this is our refrigerator, and this is our little Indiana Jones figure. So we need to find out how fast this was initially going with that acceleration. To do that, we're going to use an equation that we have from physics, obviously math-based still. So the velocity, alright, so the equation that I'm going to use is V equals VI plus AT. Now, if I explain this equation, V final, that's your final velocity. That's when everything's at rest and everything doesn't really obtain anymore because what's happened is over. The initial velocity is what you're looking for, where this is initial and going, because it's what happens first. Now, to figure this out, all we're going to do is we're going to make an assumption that the contact of so when the plume of the nuclear explosion hits the refrigerator, we're going to assume that took at a t equals 0.050 seconds. That's how much time the contact in between the force of the nuclear explosion and the refrigerator took. Now, to do this, all we're going to do is we know the acceleration, because we solved for it in this first part right here. And we know the time that it took. So we can find the final velocity, because we know that when this all started, before the nuclear explosion happened, that refrigerator was sitting, it wasn't moving, it wasn't doing anything. So we can assume that this is 0. Because it was sitting in its rest position. So we know that the final velocity equals 0, because that we just talked about the initial velocity, plus the acceleration, which is right here, 72,017.68, multiplied by how fast it's going. Or the time, I should say. Rather. When you do this, you get a final velocity of 3,600 0.88 meters per second. Now, when we solve for this velocity right here, this is the velocity that this thing's shooting out at. That's the velocity, that's how fast, with that part of a nuclear explosion, that's how fast this would initially take off and go. Now, this is where things get a little more tricky, because now we need to figure out how far this thing went to see how realistic it truly is. So to do this, we have to split it into its components. So if I redraw this, because we don't need that anymore. So I'm going to redraw this up here. Right here, this is our triangle. This is our refrigerator. This is Indiana Jones. Now, what we need to do is we need to figure out how fast Indiana Jones and his refrigerator are going when it's along this x-axis right here. That's what we need to figure out. Because this thing's going to go up, it's going to come down, and then there's a point in the middle where it'll change directions and start heading towards the ground. What we want to do is, our main goal here is to find out how far this thing went, to see how realistic this truly is. So what we got to do is we have to split it into its components. So you know that right here, we're going to call this our velocity triangle. This is our v of t triangle. So what we're going to do here is we're going to solve for all the velocities so that we know how fast Indiana Jones is moving if it was going on a flat surface. We're also going to solve for how fast Indiana Jones would be going straight up.